So this is week 4 of Applied Thermodynamics course. Uh, so this week we'll see for control volumes how to do an exergy balance and exergy destruction, exergy efficiency and so on. So I have prepared some problems on an open system or a control volume system. So we'll look into some of the problems. So the first problem for an open system is we have a refrigerant R134A at 10 degrees Celsius and 1.8 bar, and it has a mass flow rate of 5 kg per minute. This is entering an insulated compressor which is operating at steady state and exits at 5 bar. The isentropic compressor efficiency is 76.04%. So determine the temperature of the refrigerant exiting the compressor, B, the power input to the compressor, C, the rate of exergy destruction, and lastly ignore the effects of motion of gravity, and the ambient dead state conditions are T0 is 20 degrees Celsius and P0 is 1 bar. So that's what is given. So what you have is a compressor. So you are compressing a fluid, so which is coming in at 10 degrees Celsius and 1.8 bar, and you are compressing it to 5 bar. So during this compression you are having an isentropic efficiency of 76%, and you have to find out the exit temperature and how much power is taken up by the compressor, and what is the exergy destruction during this process. So we'll see how to solve this problem. So this is how the process looks in a TS diagram. So your compressor inlet is at state 1, your dead state is denoted by 0, which is at 1 bar and 20 degrees Celsius. My inlet is at 1.8 bar and 10 degrees Celsius. So this if you see corresponding saturation temperature for 1.8 bar, so my inlet is 1.8 bar, so corresponding saturation temperature is minus 12.73. Since my inlet to the compressor is at 10 degrees Celsius, so there is a superheating. So close 22.73 degrees Celsius is superheating. So I am lying here at state 1. So ideally we should have a isentropic compression. So we will go along a isentrope. So entropy will remain constant and will reach 2s, but the compressor is not 100% efficient. So isentropic efficiency is given. So it will follow path 1 to 2. So we can estimate 2 with respect to with using the compressor efficiency and 1 to 2s enthalpy difference. So I can find out 2. So from there I know the pressure to 5 bar. So and the enthalpy, I can estimate the temperature. So if you see at the inlet, it is at superheated and my enthalpy is 259.41 kilojoule per kg, and my entropy at this point is 0.9998 kilojoule per kg Kelvin. So if I would have followed as isentrope, a constant entropy line, I would reach state 2s. So this I know now two properties: one the entropy, other is pressure. So corresponding to entropy of 0.9998 and pressure of 5 bar, I can estimate my enthalpy here at 2s. So H2s is 282.7 kilojoule per kg, and if my compressor is not 100% efficient, so it will compress to state 2, which is again same pressure 5 bar, but it will have a higher enthalpy here. So that I can estimate using the compressor efficiency. So if you see in my dead state enthalpy and entropy for refrigerant R134A, my enthalpy at dead state is 270.02 kilojoule per kg and entropy is 1.0829 kilojoule per kg Kelvin. So to find out the exit temperature, I'll use the isentropic efficiency of the compressor. So isentropic efficiency is H2S minus H1, that is the ideal compression, divided by my actual compression work. So H2S minus H1 divided by H2 minus H1. So using this I know all of the values except H2, so I can estimate enthalpy at exit of the compressor. So H2 is H1 plus H2S minus H1 by the compressor isentropic efficiency. So substituting the enthalpy values here, so H1 is 259.41, my inlet enthalpy to compressor. My isentropic exit to the compressor is 282.7, and my isentropic efficiency of the compressor is 0.7604. Substituting, I will get H2 as 290.04 kilojoule per kg. So that is my enthalpy. So from the table, R134A refrigerant property table, for enthalpy of 290.04 and pressure of 5, I get my temperature as 50 degrees Celsius and my entropy at that point is 1.0229 kilojoule per kg Kelvin. So my inlet is at 10 degrees Celsius and my exit is at 50 degrees Celsius. And you see, corresponding to saturation pressure, the saturation temperature is 15.74 for 5 bar. So if you are to find out the work required in the compressor, so if you apply a steady flow energy equation, so this is what you get. So Q minus W plus your inlet energy stream and minus exit energy of the stream. So this has enthalpy, your kinetic energy and potential energy. So if you neglect kinetic and potential energies, and since the compressor is insulated, so that's what is given, we have an insulated compressor. So your Q is also 0. So in that case, my compressor work becomes m dot H1 minus H2. So substituting the values here, so I get inlet enthalpy is 259.41, my exit enthalpy I have found out to be 290.04, and the mass flow rate is 5 kg per minute, and converting it to per second I have divided by 60. So that's what I did. So this will give me the work required for the compressor is 2.55 kilowatt. So if you see minus, the minus indicates that work is being supplied to the compressor. So minus 2.55 kilowatt is the work required by the compressor. Next is we need to find out the exergy destruction, the rate of exergy destruction in kilowatt for this process. So the rate of exergy destruction is nothing but P naught into your entropy generated. So if you do an entropy balance across for this process, so what you get is for entropy balance is 0 ds by dt, so that since it's a steady flow steady state process, your ds by dt is 0, so this will become equals 0 equals summation of q by t plus your entropy coming in because of the inlet stream and entropy going out of the exit stream plus the entropy generated. So your entropy generated is then, since it is an insulated compressor, there is no heat transfer or heat interaction between the compressor and the surrounding. So Q is 0 here. So this is nothing but entropy generated is mass into my entropy of the exit minus inlet. So entropy generated then is 5 into my exit entropy is 1.0229 and my inlet entropy is 0.998. So that gives me my entropy generated is 0.001925 kilowatt per Kelvin. So in this case, substituting these values in the exergy restriction. So exergy restriction is T naught into, so as the ambient temperature in Kelvin, into my entropy generated. So 293 plus 20 Kelvin is my dead state temperature or ambient temperature into 0.001925 will give me 0.5640 kilowatt. So .04 minus 259.41. So actually, so if you find out, this will come out to be the difference between my compressor isentropic efficiency work and my actual work. So this is the exergy destruction. So T naught times my entropy generated. So in this case, the entropy generated is simple. Since it is a steady state process and there is no heat interaction, so this is just the entropy difference between the inlet and exit stream. So that gives me my exergy destruction as 0.5640. So next is we have a process across a valve. So we have a water vapor which enters a valve with a mass flow rate of 2 kg per second and a temperature of 320 degrees Celsius and a pressure of 60 bar and undergoes a throttling process to 40 bar. So what we have given is, we have given a mass flow rate and the inlet and inlet conditions, which is 320 degrees Celsius and 60 bar, and it is throttled to 40 bar. So we need to find out the flow exergy rates at the valve inlet and the exit, and how much exergy destruction is happening in the valve. Next is evaluating exergy at 8.5 cents per kilowatt hour. So determine the annual cost. So here the problem is given in dollars per year. So 100 cents is $1. So assuming associate with exergy destruction, so we can for simplicity we can say 8.5 paise and rupee. So because in 100 paise is 1 rupee, you can do it like that also. So assuming to 8,400 hours of operation annually, let T naught is 25 degrees Celsius and P naught is 1 bar. So at the inlet the water is superheated vapor. So my from steam table I get enthalpy as 2952.6 kilojoule per kg and entropy as 6.1846 kilojoule per kg Kelvin. So water at the reference state is a compressed liquid. So from table it's 25, T naught is 25 degrees Celsius and my enthalpy is 104.89 kilojoule per kg, and corresponding my entropy is 0.3674 kilojoule per kg Kelvin. So I know the dead state enthalpy and entropies, and I know the inlet enthalpies. With this I can find out the exergy at the inlet. So before that we have to find out flow exergies at inlet and outlet and exergy rate. We have to find out the exit one. So since it's an throttling process, to apply a steady flow energy equation, So this is what we get, Q minus W plus mass energy in and minus energy out the streams. So if we neglect the kinetic energy and potential energies, and since there's a valve, there is no heat interaction and there is no work interaction, so I'll get H1 minus H2 is equal to 0. So it's an isenthalpic process now. So my inlet enthalpy is what my exit enthalpy is. So I know enthalpy at exit, and I know the exit pressure as 40 bar. So from the table for enthalpy of 2952.6 and 40 bar, I get entropy as 6.3456. So now I know the inlet enthalpy and entropy and exit enthalpy and entropy. So now I can estimate my flow exergies. So flow exergy at inlet is nothing but H minus T naught S is my exergy. So minus my exergy at a dead state. So m dot H1 minus H naught minus T naught S1 minus S naught. So substituting the values here, I get with the mass flow given as 2 kg per second. So I get exergy, flow exergy at inlet is 2228.4 kilowatt, and similarly I can estimate the flow exergy at exit. Exit flow exergy is again m dot H2 minus H naught minus T naught S2 minus S naught. So flow exergy is again mass into my values, substituting the values, I get 2132.4. So with this I can find out the rate of exergy destruction. So exergy destruction is nothing but my exergy coming in minus going out minus exergy destroyed. Since it's a steady state process, there is no change in exergy dou E by dou T. So this is what exergy what is coming in and exergy what is going out. The difference will give me the exergy destroyed. So exergy destroyed is flow in minus flow out exergies. So substituting the values, I get exergy destroyed as 96 kilowatt. So in terms of cost, if you see in this process what your what exergy loss is happening, if you convert it into cost, it's 96 kilowatt into you are spending 8.5 cents per 5 paise per kilowatt hour, and the total 8,400 hours in a year, and 1 cent is 100, 1 paise is say 100 rupees. So in that case you'll get 68,544 per year. So that's how much you have to bear in a cost, if you in a perspective. So what it says is you have to spend this much to again bring it back to the same state. So this is going from our pocket to bring the state of the fluid at state 2 to state 1. So the next is we saw a turbine, we saw a valve. Next we will see a heat exchanger. So how to do an exergy balance across heat exchanger. So a counterflow heat exchanger operating at steady state has water entering as saturated vapor at 5 bar with a mass flow rate of 4 kg per second and exiting as saturated liquid at 5 bar. So air enters in a separate stream at 320 Kelvin and 2 bar and exits at 350 Kelvin with a negligible change in pressure. Heat transfer between the heat exchanger and its surrounding is negligible. So determine the change in the flow exergy at each stream, the rate of exergy destruction in the heat exchanger. So the dead state condition is T naught is 300 Kelvin and P naught is 1 bar. So what is happening is we have heat exchanger here. So you have a saturated vapor coming in at 5 bar and going out as saturated liquid. So this is getting cooled, and in the process air is getting heated. So air is cooling your refrigerant or water. So air is at 320 Kelvin and 2 bar, and it's going out at 350 bar and 2 bar. So you are condensing water, it's like condenser, you are condensing water from a saturated vapor to saturated liquid with cooling it with in a heat exchanger. So this is how it looks. You know the inlet and outlet conditions. So we'll see how to find out the exergy destruction in a heat exchanger. So first the mass is constant, so it's a steady process. So mass coming in is what is mass going out for water. So m dot 1 and m dot 2 is the mass of water, and similarly m dot 3 and m dot 4 is the mass of flow rate of air. So if we apply an energy balance, so Q and W is 0, so there is no any heat or work across the boundary. So it is happening inside the streams. So there is heat transfer between water and air, but it's not crossing the boundary. So your Q is 0 and W is 0, and the inlet stream minus exit stream, so m dot h1 minus h2 plus m dot a h3 minus h4 is what we get from a steady flow energy equation. So from this we can get a relation between mass of air and mass of water. So m dot a is m dot of water into h1 minus h2 divided by h4 minus h3. So h1 minus h2 is my latent heat at 5 bar, which is 2108.5, and for h4 minus h3, this is can take Cp into delta T, or can use R chat to find out the enthalpy, and that will give me mass of air. Mass of water is given as 4 kg per second. So using that we can find out the mass of air, which is 279.27 kg per second. So the flow rate exergy change in for water stream is the exergy out of water minus exergy flow exergy in. So this will give me m dot W h2 minus h1 minus t naught h2 minus h1. So mass of water is 4, and the enthalpy value substituting, I'll get exergy change is minus 2481.4 kilowatt, because I am condensing the vapor to liquid. So my enthalpy is reducing. Essentially what is happening is I am cooling the water, so there is a loss in exergy. So I am using minus 2481.4 kilowatts in the process, and for the air stream, the change in exergy is the exergy out minus exergy in. So mass of air into h4 minus h3 minus t naught h4 minus h3 minus r ln p4 by p3. Since this pressure is negligible change, so this becomes 0. So substituting, I get substituting the values, I get exergy change in the air stream is 878.58 kilowatt. You see this is positive because air is getting heated, so it's going from a lower exergy state to a higher exergy state, and this because this is at temperature is more than the dead state temperature. That's why my exergy is increasing. So it is 878.58 kilowatts in the air stream. So if you see, if you do an exergy balance across the heat exchanger, so Q1 minus T naught by T, so this is the ideal work which you will get from for a heat source, minus W minus P naught dV. So this is the work done on atmosphere. the work which I am getting minus WCV, then the exergy coming in and exergy going out. So in this case QW and P naught dV by dt is all 0. So exergy coming in minus exergy going out is equals to exergy destroyed. So exergy destroyed is exergy flow change of the water minus exergy flow rate change of my air. So substituting, I'll get minus of minus 2481.4 minus 878.58. So this will give me 1602.82 kilowatt. So this much amount of exergy has been destroyed. So if you see, the decrease in energy in the water stream exactly equals the increase in energy in the air stream. So there is an energy balance, but there is no exergy balance. So because both are at different temperature levels, even though there is energy balance, but ultimately there is exergy destroyed because there is entropy generation during the process. So since both the streams are at different temperature, so heat is flowing across the temperature difference, so which will create entropy, and that is causing this exergy destruction. So moving on to next question. We have steam at 30 bar and 700 degrees Celsius, which is available at one location in an industrial plant. So we have steam at 30 bar and 700 degrees Celsius. At another location, steam at 20 bar and 400 degrees Celsius is required for use in a certain process. So an engineer suggests that steam at this condition can be provided by allowing the higher pressure steam to expand through a valve to 20 bar and then cool to 400 degrees Celsius through a heat exchanger with heat transfer to the surrounding, which are at 20 degrees Celsius. So you have steam at 30 bar and 700 degrees Celsius, but you require steam at 20 bar and 400 degrees Celsius. So you have a higher exergy stream and you want it at a lower exergy for the process, some process. That's the condition at which your steam is required. So what the engineer suggests is you can do a pass it through a valve to throttle it to 20 bar, and then this will be temperature will be still higher than 400 degrees Celsius. So cool it in a heat exchanger to 400 degrees Celsius and reject this heat to the ambient. So my ambient is at 20 degrees Celsius. So doing this, process, you are getting to 20 bar and 400 degrees Celsius. So what we have been asked is evaluate this suggestion by determining the associated exergy destruction rate per mass flow rate of steam. So what is the exergy destruction for this process, and suggest an alternate method for obtaining steam at the desired condition that would be preferable thermodynamically of the exergy destruction for a mass flow rate of 1 kg per second. So this is the process which has been suggested. So to pass it across a valve and then to a heat exchanger, and then you are getting it at 20 bar and 400 degrees Celsius. So initially you are at 30 bar and 700 degrees Celsius. You are throttling across the valve to 20 bar, and then you are ejecting heat to 20 bar and 400 degrees Celsius. So in a HS diagram, this is how your the process is. So you have 20 bar line and a 30 bar line. So initially you are at 30 bar, so you are throttling it, so it's a constant enthalpy process from 1 to 2, and then you are rejecting heat to come to state 3. So for the valve, if you see the rate of exergy destruction, so same as the previous problem for the valve. So this is per mass flow rate is your entropy change across the valve. So that is the entropy generated, and the exergy restriction is T naught times the entropy generated. Since state 2 is fixed, so my enthalpy is it's a constant enthalpy process. So my state 2, I know it is enthalpy at state 1 and 20 bar. So enthalpy at state 1 is 3911.7 kilojoule per kg, and then from table we get entropy at state 1 is 7.7571 kilojoule per kg Kelvin, and for state 2, for this enthalpy of 3911.7 and the pressure of 20 bar, I get entropy as 7.9427 kilojoule per kg Kelvin. So I know both entropies at inlet and exit of the valve. So my exergy destroyed will be T naught times entropy generated, which is T naught times the entropy change. So 293 into specific entropy change is 7.9427 minus 7.7571 gives me 54.38 kilojoule per kg. So that's the exergy destroyed across the valve, so which is 54.38 kilojoule per kg. So now we need to estimate the exergy destroyed across the heat exchanger. So since heat transfer of the stream goes from state 2 to state 3 and it is not being used, so if you apply, so there is a heat transfer, and that we can equate it to the heat gained by the surrounding. So that is happening at constant temperature. So if we do an exergy balance, so Q 1 minus T naught by T naught, that will be 0. So it ultimately says that heat is directly rejected to ambient, so you are not getting any work out of it. So that heat is of no use to us. So that essentially convert it to 0. So that's, there is no exergy or any use obtained out of rejecting heat to the ambient. So minus W. So here in heat exchanger there is no work transfer, so that is 0. So plus my exergy change of the streams minus exergy destroyed. So exergy destroyed is nothing but the exergy change in the stream. So exergy destroyed per mass flow rate is H2 minus H3 minus T naught H2 minus H3. So substituting the values, I get exergy destroyed is 425.13 kilojoule per kg. So if you see, so there are two significant exergy destruction process. So one is because of the expansion in the valve, and the other is because of the heat transfer in the surrounding. So if you see, compare both exergy losses in across the valve, which is 54.38, and heat exchanger 425.13. So there's a large exergy destruction across the heat exchanger. So ideally speaking, this has to be changed. So to see, so initially we'll convert the valve to a turbine. So if we are replacing valve with the turbine, so this is what happens. So initially at state 1, and we are going to state 2 dash, and then we are rejecting to 3. So instead of following an isenthalpic process, now we are following an isentropic process. So 1 to 2 dash, ideally it should be isentropic, but it will not be isentropic. So it goes 1 to 2 dash, and then 2 dash to 3. So we are assuming we are having a turbine efficiency of 80%, So my specific enthalpy and entropy at state 2 dash will be, so same as what we saw in the compressor case. So turbine efficiency will be actual minus actual divided by the isentropic work generated in the turbine. So it will be H1 minus H2 dash divided by H1 minus H2s. So substituting and XG efficiency, I get H2 dash, which is 3773.5 kilojoule per kg. So I know now enthalpy at the exit of the turbine, and the pressure is at 20 bar. So corresponding to these two enthalpy and pressure values, my entropy at exit will be 7.7958 kilojoule per kg Kelvin. So the XG destruction in turbine is now T0 S2 dash minus S1. So I get T293 into 7.7958 minus 7.7571. So that will come out to be 11.34 kilojoule per kg. So if you see now, the XG destruction replacing valve with turbine has come down from 54.38 to 11.34 kilojoule per kg. So there is a significant drop by changing the valve to a turbine, but this comes as a cost. So we will see later. So what happens is, initially we are at 2 dash now. So what happens to the heat exchanger? So heat exchanger, my destruction in heat exchanger is XG destruction. So H2 dash minus S3 minus T0 H2 dash minus S3. So previously H2 was 3911.7, so now it has come down to 3773.5, so minus 324.7.6, and similarly substituting entropy values, I get XG destruction at 329.97 kilojoule per kg. And if you see, in the previous case it was at 425.13 kilojoule per kg. This is because my inlet to the heat exchanger, when the valve was considered, was at higher temperature compared to a turbine here. So this is at lower temperature, so my XG is lower to the heat exchanger in the second case. So because of that, my XG drops. So I have to reject lesser amount of heat in a heat exchanger. Because of that, so that has reduced my XG destruction in the heat exchanger to 329.97. So changing from valve to a turbine has reduced both XG destruction in a valve process and the heat exchanger. So if I have changed heat exchanger, just the heat exchanger, then the XG destruction across the valve would have remained same. So that's why first we have changed the turbine, valve to a turbine. So, but what is the consequence practically? If you see, valve is a simpler device, there is no moving part, so it has greater reliability. But turbine, also valve costs less compared to a turbine. So turbine, initial capital cost for the turbine is more, so that comes into play. So then the return of investment, the other picture comes into play going through the process. So a company may choose the first one compared to the second based on their return of investment and how they can use the money and so on. So if whatever work is generated and this thing money and the return period is larger, then they may not go with the turbine, but even though this is a better efficient process compared to the previous process one. And how can we improve it more? Depends upon the temperature. So here if you see, you are rejecting this process heat exchanger, the minimum temperature if you see, it's at 400 degrees Celsius, but your inlet temperature will be much more higher to 400 degrees Celsius. So if you run a heat engine with the heat exchanger, coupled with the heat exchanger, and not reject heat to the ambient, so you will develop some more work. So now you are not ejecting directly to the ambient, but you are running heat engine and then rejecting some part of the heat to a ambient. So that will reduce your exergy restriction across the heat exchanger a little bit more. So even more, then your totally exergy restriction will come down. So that is the second part which can be done. So again, that will cost money, adding a heat engine and so on. So even though the operating cost comes down, my capital cost will increase. So there is a cost picture, but again compared to efficiency. So I'll try to push it to a higher efficient process by reducing the exergy destruction and so on. But my initial capital cost is also increasing because of that. So with that, we'll move on to the next question. So we have a nitrogen which is at 25 bar and 450 Kelvin. This enters a turbine and expands to 2 bar 250 Kelvin with a mass flow rate of 0.2 kg per second. So the turbine operates at steady state with negligible heat transfer with its surrounding, assuming the ideal gas model with K of 1.399 and ignoring the effects of motion of gravity. Determine the isentropic turbine efficiency, the exergetic turbine efficiency, and your ambient conditions are 25 degrees Celsius temperature and pressure of 1 atmosphere. So what is given is there is nitrogen at 25 bar and 450 Kelvin to the inlet to the turbine, and it is expanding to 5 bar and 250 Kelvin. So we need to find out, so we can assume it to be an insulated turbine. So that's what we are saying, the negligible heat transfer. So there is no heat transfer between the turbine and the surrounding. So there is only work transfer. So we have to find out what will be the isentropic efficiency and the exergetic efficiency. So we'll see how to solve this. So if we see, this is how the process looks. So this is the turbine. So inlet is at 25 bar and 450 Kelvin, and mass flow rate is 0.25 kg and 0.2 kg, and my exit is at 2 bar and 250 Kelvin, and I am getting work output. So in a TS diagram, so initially I am at state 1 here, and if I expanded it isentropically, I will reach here state 2s. But since this turbine is not efficient, 100% efficient, so if you run 100% efficient, my 2 bar 250 Kelvin corresponding to these two properties, my state point 2 will have entropy same as entropy at the inlet. So in that case, my turbine is 100% isentropically efficient. But if it's not, I'll reach state 2. So I have to find out this isentropic efficiency. So how will I do that? For turbine, my isentropic efficiency is my actual work divided by my isentropic work. So actual work is H1 minus H2. My isentropic work will be H1 minus H2S. So assuming this is nitrogen, so assuming it to be an ideal gas or a calorifically perfect gas, so I'll Cp T1 minus T2 divided by Cp T1 minus T2S. Cp is constant, assuming Cp is constant, so Cp will go, so I'll get T1 minus T2 by T1 minus T2S, or we can directly use a nitrogen chart to find out enthalpies. So here we are assuming it with Cp is constant, So I can find out 2 T2S from for an isentropic process, since gamma is value is given, or the adiabatic index value is given is 1.399 or 1.4. So T2S is T1 by T1 into P2 by P1 raised to power gamma minus 1 by gamma. So substituting the values, so T1 is 450 Kelvin and P2 is 2 and P1 is 25 bar. So and my gamma adiabatic index value is 1.399. Substituting, I get T2S as 219 Kelvin. So but my outlet is 250 Kelvin. So substituting it in the exergy isentropic efficiency formula, I get isentropic efficiency of, so this is 450 minus 250, which is 200, divided by 450 minus 219. So I get 0.87. Exergy efficiency of isentropic efficiency of 0.87. Now I have to find out the exergy efficiency of the compressor. So to find out exergy efficiency of the compressor, I will write my actual work divided by my reversible work which I have to do. So my actual work is H1 minus H2, and reversible work is my exergy change across the compressor. So H1 minus H2 minus T naught S1 minus S2. So H1 minus H2 I can write it as Cp T1 minus T2 divided by Cp T1 minus T2 is H1 minus H2 minus T naught and delta S. So delta S is for two states, the change in entropies Cp ln T1 by T2 minus R by M ln P1 by P2. So this is what I get. So substituting the temperature and pressure values, and Cp I can find from using Cp and R. R is Cp gamma minus 1 by gamma. So substituting that in the expression, so this is what I get. I can Cp gets cancelled out to get all on the numerator and the denominator. So substituting the temperature and pressure values, I get the exergy efficiency of 0.835 or 83.5%. So the isentropic efficiency is 87% and exergy efficiency is 83.5%. So moving on, steady state operating data. Is shown in figure for open feed water heater. So heat transfer from the feed water heater to its surrounding occurs at an average outer surface temperature of 50 degrees Celsius at a rate of 100 kilowatt. So I'll just add upon this. I forgot to add. So if you see normally why my exergy efficiency and isentropic efficiency is different. So normally speaking, if I would have state is 2s, then it would have been isentropic efficiency. So in isentropic efficiency, my exergy efficiency will also always be 1. If my isentropic efficiency is 1, my exergy efficiency will also be 1, because my entropy generated entropy change is 0 here. So this will be 1. So in this case, if I have to go from 2 to 1. So isentropic efficiency is comparing between process 1 to 2 and 1 to 2s, but exergy efficiency here is comparing between 1 to 2 and doing a reversible process to go from 2 to 1. So in that case, what would have been my work done? So that is what is given by the exergy efficiency here. So that's why these two are different. So that it's comparing between 1 to 2 and 1 to 2s. Here this is same between state 1 to 2. So my exergy, my work done between 1 to 2, and what would have been reversible work, which I would have got if I going from state 1 to 2. So that's the difference. Okay, so going to the next problem, we have steady state operating data as shown in figure for an open feed water heater. So heat transfer from the feed water heater to its surrounding occurs at an average outer surface temperature of 50 degrees Celsius at a rate of 100 kilowatt. So ignore the effects of motion and gravity and let P naught be 25 degrees Celsius and P naught at 1 bar. Determine the ratio of incoming mass flow rates M1 by M2 and the rate of exergy destruction in kilowatt. So this what is happening. So there's an open feed water heater. So there's a mass of 0.7 kg per second and the pressure of 1 bar and 40 degrees Celsius coming in, and there's a mass coming in with pressure of 1 bar and 400 degrees Celsius, and this is getting mixed and going out at both mass M1 plus M2, and my dryness fraction here is 25% and my pressure is 1 bar. So basically you are mixing a steam with water, and this is water is getting converted into steam in the process, but at a lower temperature, and you are getting some steam plus water mixture out, and this open feed water heater is at 50 degrees Celsius and it is rejecting heat to the ambient, which is 100 kilowatt. So for this we need to find out the mass and then the exergy destruction. So this is how the process looks in a TS diagram. So this is all happening at a constant pressure, so all are at 1 bar. So my dead state is at 25 degrees Celsius here, and my inlet is at water is at state 1, 40 degrees Celsius is here, and my other inlet is at 400 degrees Celsius and state 2. So these two are getting mixed and going out at state 3, which is a two phase condition with 25% of dryness fraction. So for this we will do. So once we apply energy balance across the open feed water heater, so what we get is Q minus W plus mass enthalpy coming in minus enthalpy energy going out. So Q plus m dot 1 H1, which is coming in, plus m dot 2 H2 minus m dot 3 H3. So m dot 3 is m dot 1 plus m dot 2. So substituting that and rearranging, we can find out m dot 2. So m dot 2 is m dot 1 into H1 minus H3 plus Q. Q is the heat which is getting ejected to the ambient, divided by H3 minus H2. So we get from the steam table, we can find out H1, which is 167.57, and H2, which is 3278.2 kilojoule per kg, and H3 also we can find out because we know dryness fraction, and one saturated liquid and vapor enthalpies can be found out. So from there we can find out H3 is 981.96 kilojoule per kg. So using this and substituting, we know mass at inlet of stream 1 is 0.7 kg per second, and Q is rejected, which is minus 100 kilowatt. So rejected, that's why negative. So substituting, we get mass as 0.292 kg per second. So we then asked to find out the mass ratio. So m dot 1 by m dot 2 is 0.7 by 0.292, which is 2.4. So next we need to find out the exergy destruction in the process. So for that we'll do an entropy balance to find out the entropy generated. So entropy generated is exergy destruction is T naught times entropy generated. So doing an entropy balance, so entropy generated is minus Q by T. So minus entropy coming in and plus entropy going out. So entropy in for stream 1 is 0.5725, and at S2 is 8.5435, and S3 is the two-phase condition. So there with the dryness fraction I find out the entropy to be 2.8168, and mass 3 is the summation of both the inlets is 0.7 plus 0.292, so comes out to be 0.992 kg per second. So substituting all, and my surface temperature is 50 degrees Celsius, so this is 323, so minus Q by T of the surface. So here Q is negative because it is getting rejected, so minus minus will get plus, so 100 by 323 minus my inlet and exit entropies, so it will give me entropy generated as 0.20841 kilowatt per Kelvin. So now the exergy destruction becomes T naught times sigma, which is 298 into 0.20841, so comes out to be 62.11 kilowatt. So next question is, so in the boiler of a power plant are tubes through which water flows as it is brought from 0.6 megapascal and 130 degrees Celsius to 200 degrees Celsius, essentially at constant pressure. Combustion gases with a mass flow rate of 400 kg per second pass over the tubes and cool from 827 degrees Celsius to 327 degrees Celsius and at constant pressure. The combustion gas can be modeled as air behaving as an ideal gas. There is no significant heat transfer from the boiler to its surrounding. Assuming steady state and neglecting the effects of motion and gravity, determine the mass flow rate of the water, the rate of exergy destruction, and the exergy efficiency. So T naught is 25 degrees Celsius and P naught. So this is basically a fire. It's a boiler. So it's a water tube boiler. So you have water flowing across the tubes, and it's a combustion gas which is flowing above these tubes, and these are heating the water which are there inside the tube. So they are converting it to steam. So this water is at 6 bar and it is heated from 130 degrees Celsius to 200 degrees Celsius, and in the process the air is getting cooled from 827 to 327 degrees Celsius. So we will see how to solve this. So my enthalpy and entropy values are all given for each of the states. So if you see air which is at 110 Kelvin, my enthalpy is 1161.07, the entropy is 3.07732, and similarly for 600 Kelvin it's 607.02, and entropy is 2.409. And for waters, similarly, enthalpies and entropies are given. So if we do an energy balance across the boiler, I get mass of the combustion gases into enthalpy difference equals mass of water into enthalpy difference. So we'll get mass of water as mass of combustion gases into H2 minus H1 divided by H3 minus H4. So substituting the enthalpies and water mass of combustion gases is 400 kg per second, I get mass of water as 96.2 kg per second. Then we can find out the exergy destruction. So exergy destruction is similar to what we did in the heat exchanger problem. So it's just the exergy difference of the inlet and outlet streams. So exergy change of the combustion gas plus exergy change in the water. So exergy change in the combustion gases is H1 minus H2 minus T naught S1 minus S2. Since it's a constant pressure, so there is no entropy change here. This will be 0. So substituting the values, I get exergy changes 354.9 kilojoule per kg, and exergy change in the water is H3 minus H4 minus T naught S3 minus S4. So substituting the values, I get minus 712.9 kilojoule per kg. So here we are doing inlet minus exit. So actually, if you see, we were sort of doing exit minus inlet. So here, because of the negative sign and rearranging, we get inlet minus exit. So exergy destruction is exergy in minus exergy out. So we are doing in minus out. So here exergy change of gas combustion gas, we are showing getting positive because my inlet is at higher exergy, and similarly for water my exit is at a higher exergy because they convert it into steam. So that's why it is negative. So the combined exergy destruction, substituting the values, I get 73379 kilowatts. So that is the exergy destroyed. So exergy efficiency is nothing but exergy of the stream outlet useful effect. So here my useful is converting it to steam in the boiler. So exergy of the water, change in the water divided by exergy change in the air. So instead of heating water, if I have used it to generate work, so I would have got some work. So now that has reduced it to exergy of the water. So that's why we are doing exergy change of water divided by exergy change in the combustion gas. So 96.2 is the mass into exergy change in water is 712.9, and exergy change in combustion gas is 400 into 354.9. So this gives me exergy efficiency of 48.3%. So moving on to next question. A 4-liter pressure cooker has an operating pressure of 175 kilopascal. So initially half of the volume is filled with liquid water and the other half by water vapor. So the cooker is now placed on top of a 750 watt electrical heating unit that is kept on for 20 minutes. Assuming the surroundings to be at 25 degrees Celsius and 100 kilopascal, determine the amount of water that remained in the cooker, the exergy destruction associated with the entire process, including the conversion of electrical energy to heat energy. So what is happening is we have 4-liter pressure cooker, and the operating pressure is 175 kilopascal, so that is 1.75 bar. So initially half of the volume is filled with water and the other half is water vapor. So we are using a electrical heater which has a 750 watt heating capacity, and it is on for 20 minutes. So assuming the surrounding to be at 25 degrees Celsius and 100 kilopascal, we need to find out the amount of water that is there in the cooker and exergy destruction. So we'll see how to solve this. So pressure is 175 kilopascal. So corresponding saturated liquid and vapor specific volumes are 0.001057 meter cube per kg and 1.0037 meter cube per kg. And similarly, I am finding out my internal energies and entropies. So my after that, my stream which is coming out, so it's a pressure cooker and we are heating it. So in the process, what will happen is we have to maintain it at 175 kilopascal. So the exit is coming in at 175 kilopascal. So exit enthalpy is at 175 kilopascal saturated vapor. So the enthalpy is 2700.2 kilojoule per kg and entropy is 7.1716 kilojoule per kg Kelvin. So if we do a mass balance across for the process, so mass coming in minus mass going out is the mass change in the system. So since there is no mass coming in but there is mass leaving, so mass exit is the mass at state 1 minus mass at state 2. So that's what we get from the mass balance. And if you do an energy balance, so E in minus E out is the energy change of the system. So W E in minus M dot E H E equals M dot 2 U2 minus M dot 1 U1. So W is the electrical energy which you are supplying. So we have to find out the initial and mass. So initial mass, initial internal energy, and the initial entropy and final mass have to be found out. So initially we know it is a 4 liter tank. So half of it is filled with water and half by water vapor. So 2 liter is filled with water and 2 liter is filled with gas. So mass M1 is M dot F by M dot G, which is volume divided by specific volume of liquid, and volume occupied by gas divided by specific volume of gas. So this will come out to be 1.8945 kg. So that is the amount of mass which is present initially. Similarly, U1 is mass times the specific volume. So individual mass of water into saturated internal energy of liquid. Similarly for gas, so I'll get internal energy at state 1 is 926.6 kg and entropy is 2.8239 kilojoule per kg, kilojoule per Kelvin, and mass of 2 is my volume divided by specific volume. So my volume is 4 liter, so 0.004 meter cube divided by specific volume, so which we have to find out. So amount of electrical energy which we have given is 750 watts into delta T. So this is given for 20 minutes. So 20 into 60 will give me 900 kilojoules. So 900 kilojoules of energy has been supplied. So substituting it in the mass balance and energy balance expressions. So this is what we get. WE is 900 kilojoules and ME is the mass exiting, M1 is 72, and HE is my saturated vapor enthalpy, and M2 U2 minus M1 U1. So substituting U2 as saturated liquid and saturated vapor, and similarly my specific volume at 2 as in terms of dryness fraction and specific volume of vapor and liquid, saturated vapor and liquid, and the expression will convert to a single variable of dryness fraction. So the only unknown will be dryness fraction. So solving for that, we will get x as 0.001918. So that is the dryness fraction. So substituting, I get specific volume and entropy at state 2. So specific volume is 0.002654 meter cube per kg and entropy at exit is state 2 is 1.5642. So with this I can find out mass at 2 is 0.004 divided by 0.002654. This gives me 1.507 kg. So initially it was 1.8945 kg. Now we have 1.507 kg. So during this process the entropy generated is S in minus S out plus S generated equals the entropy change in the system. So entropy in is 0, entropy exit is m dot ESC plus entropy generated equals entropy generated in the system is m2 S2 minus m1 S1. So this is what we get. So exergy destroyed is T naught MESC, the exit stream entropy plus entropy change in the system. So substituting the values we will get exergy destroyed as 689 kilojoules. So moving on to next question. We have refrigerant R134A enters a counterflow heat exchanger operating at steady state at minus 32 degrees Celsius and a quality of 40% and exits as a saturated vapor at minus 32 degrees Celsius. So air enters as a separate stream with a mass flow rate of 5 kg per second and is cooled at a constant pressure of 1 bar from 300 to 250 Kelvin. Heat transfer between the heat exchanger and its surrounding can be ignored, as can the effect of motion and gravity. A. Sketch the variation of temperature of each stream along the length of heat exchanger. Locate T naught on the sketch. B. Determine the rate of exergy destruction within the heat exchanger in kilowatt. C. Devise and evaluate an exergetic efficiency for the heat exchanger. So this is how the process is. We have a heat exchanger. So inlet is at minus 32 degrees Celsius and dryness fraction of 40%, and exit is at saturated vapor. So air is coming at 300 Kelvin and 1 bar and going out at 250 Kelvin. So air, we are basically cooling air. So we are cooling air from 300 Kelvin to 250 Kelvin. So if you see in a TS diagram, we are at minus 32 here and my dead state is at 1 bar and 300 Kelvin. So this is how the process looks for R134A. So if we see in a heat exchanger, if you saw that see the temperature variation, since this is a pure fluid, so it boils at constant temperature. So 1 to 2, this is at minus 32 degrees Celsius, so this is constant temperature. Then air is coming in at 300 Kelvin and it's going to 250 Kelvin, and my dead state is this 300 Kelvin, the ambient air. So this is how the temperature will look. So if we do an energy balance across this heat exchanger, what I'll get is enthalpy change for R134A equals the enthalpy change of air. So that's what we get. So from there I can find out the enthalpy of mass flow rate of R134A. So m dot 1 is m dot 3 into H3 minus H4 divided by H2 minus H1. My mass of air is 5 kg per second, and substituting the enthalpy values, I'll get 1.913 kg per second. So that is the mass flow rate of refrigerant, and enthalpies and entropy value I can get it from the refrigerant chart, and for water the steam table. Then the rate of exergy destruction can be determined by reducing an exergy rate balance. So if we do an exergy balance, so exergy because of heat addition So there this is because 0, there is no heat transfer and there is no work transfer, so W is 0. So this is exergy destruction is exergy in minus exergy out. So substituting exergy in minus exergy out, so I'll get H1 minus H2 minus T naught S1 minus S2 is the exergy in minus out for R134A, and similarly exergy change for air, which is H3 minus H4 minus T naught S3 minus S4. So substituting the enthalpy and entropy values, so and mass which we have found out, so we'll get exergy destruction as 37.5 kilowatts. So next is we need to find out the exergy efficiency of the heat exchanger. So this is just like the previous one. So exergy change for my air is m dot 3 EF4 minus EF3, which is 23.6 kilowatt, and similarly exergy change for my refrigerant is EF1 minus EF2, which is 61.14 kilowatt. So if you see, air is from the dead state, it is lowered to a lower temperature, so its exergy efficiency value increases. So it is going from a lower exergy state, which is 0, to a higher exergy. And but if you see refrigerant, it is at higher exergy because it is minus 134 liquid, because it is heated, so it is being pushed towards the dead state, so its exergy is reducing. So exergy change in the air divided by exergy change in the refrigerant. So exergy change in air is 23.6 divided by exergy change in the refrigerant, which is 61.14. So that gives me 38.6%. So that is the exergy efficiency of this process. So next, I think this is the final problem which I have for today. We have a compressed air storage tank which has a volume of 5 lakh meter cube, and it initially contains air at 100 kilopascal and 20 degrees Celsius. The isentropic compressor proceeds to compress air that enters the compressor at 100 kilopascal and 20 degrees Celsius until the tank is filled at 600 kilopascal and 20 degrees Celsius. So all heat exchangers are with the surrounding air at 20 degrees Celsius. Calculate the change in the work potential of air stored in the tank. How does this compare to the work required to compress the air as the tank was being filled? So at room temperature, my R is 0.287, Cp is 1.005 for air, Cv is 0.718 and gamma is 1.4. So the initial mass of air in the tank is when it is at ambient condition, so which is 20 degrees Celsius and 1 bar. So substituting using ideal gas law, I get mass as PV by RT. So P is 100 kilopascal, V is 5 into 10 power 5 meters cube, divided by R is 0.287 kilopascal kilojoule per kg Kelvin into T 293. So I get 0.5946 into 10 power 6 kg. So that is the amount of mass of air initially present. Then the final mass in the tank is when the pressure is 600 kilopascal and temperature is 20 degrees Celsius. So same R and T, so only pressure is changing. So mass is 3.568 into 10 power 6 kg. So when the compressor is operating as an isentropic device, so my T2 is P1 into P2 by P1 raised to power gamma minus 1 by gamma. And when we do a mass balance, there is no exit to the tank, so only inlet, so that is equals to the change in mass. So of the system. So rate of change of mass is the mass flow rate to the tank. And then when we do a energy balance, so Q dot is energy change of the system equals energy in minus energy out. So energy out is Q and energy in is the enthalpy which is coming in equals the energy change. So this rearranging, I'll get Q dot is dmu by dt minus h dm by dt. So substituting the ideal gas equation, u is cvt. So substituting t as pv by r, I get v cv by r dp by dt minus cpt v by rt dp by dt. So using the temperature relation for the isentropic compressor, I know temperature at T2. So this is the expression which I get. So integrating, so I get Q, the total Q which is rejected, into V equals V Cv by R. So into change in pressure minus gamma by 2 gamma minus 1 into Cpv by R into my pressure into pressure ratio gamma minus 1 by gamma minus pressure initial. So substituting the values here, I get Qs minus 6.017 into 10 power 8 kilojoule. So that is the amount of Q heat which has been rejected. So the negative value shows that heat is rejected from the tank to the ambient. So applying the first law to the tank and compressor together, I get Q minus W dt equals dmu minus h1 dm. So after integrating, I get Q minus W, which is change in energy of the tank minus enthalpy coming in into change in mass. So substituting here, I know Q, I can find out W. I get W as minus 3.516 into 10 power 8 kilojoule. So this is the work done on the compressor for the whole process. So the negative sign shows that the work is done on the compressor. So when the combined first and second law is reduced to fit the compressor and tank system, so we'll get when you do an XCG balance, basically you get WR reversible is Q1 minus T naught by TR minus du minus T naught S by dt plus H minus T naught by S dm by dt. So this is just combining first law and the energy balance and the entropy balance. So this is what we get. So substituting the values, so the first term will become 0 because it is happening to the ambient. So this will become 0. So writing U and H in terms of Cp and Cv, and substituting the values, I get W reversible is 7.875 into 10 power 8 kilojoule. So this is the XCG change of the air stored in the tank. Okay, so this is the last problem. So nitrogen gas enters a diffuser at 100 kilopascal and 110 degrees Celsius with a velocity of 205 meter per second and leaves at 110 kilopascal and 45 meter per second. It is estimated that 2.5 kilojoule per kg of heat is lost from the diffuser to the surrounding at 100 kilopascal and 27 degrees Celsius. So my inlet is at 100 kilopascal and 110 degrees Celsius and 205 meter per second. So this is a diffuser, so my velocity will come down and my pressure will increase, because so we are converting kinetic energy into a pressure energy. So it is coming out at 110 kilopascal and 45 meter per second. So during this process there is heat rejection to the ambient. is equal to 2.5 kilojoule per kg, and the ambient is at 100 kilopascal and 27 degrees Celsius. They are given the exit area of the diffuser is 0.04 meter square. So accounting for the variation of specific heats with temperature determined. So this says that we cannot assume it as an ideal gas or a calorifically perfect gas. So we have to take the properties from the chart or a table of nitrogen, then determine the exit temperature, the rate of exergy destruction, and the second law efficiency of the diffuser, or the exergy efficiency of the diffuser. So R is 0.2968 kilojoule per kg. So for T1 is 110 degrees Celsius, which is 383 Kelvin, and pressure of 100 kilopascal. So from a table or chart, I get enthalpy as 88.39 kilojoule per kg, and entropy is 7.101 kilojoule per kg Kelvin. And similarly for T1, which is 300 Kelvin, and P1 110 kilopascal, which is the ambient condition. So H0 is, so this is T0 and P0. So H0 is 1.93 kilojoule per kg, and S0 is 6.846 kilojoule per kg Kelvin. So doing an energy balance across the diffuser, I get H1, which is energy coming in equals energy going out. So H1 plus V1 square by 2, which is the kinetic energy, plus enthalpy out stream plus kinetic energy of the outlet plus heat rejected. So substituting all the values here, I can find out the enthalpy at the exit. So enthalpy at exit is 105.9 kilojoule per kg. So the corresponding properties at the exit of the diffuser are H2 is 105.9 kilojoule per kg, and pressure is 110 kilopascal. So with this two, I can find out the temperature, which is 127 degrees Celsius or 400 Kelvin, and entropy is 7.117 kilojoule per kg Kelvin. So now I can find out mass flow rate of nitrogen. So m dot is rho 2 A2 V2. So for this case, if I substitute P rho dot as P dot P2 by RT2, or I can directly find out using this temperature what is the density at exit for 110 kilopascal and 400 Kelvin. Density, I get mass is 1.669 kg per second. So the exergy destruction in the nozzle will be m dot h1 minus h2 plus v1 square by 2 minus v2 square by 2 minus t naught s1 minus s2. So that is exergy in minus t naught s1 minus s2. So energy in minus t naught s1 minus s2. So I get exergy destroyed as, substituting the values, 12.4 kilowatt. So additionally there will be Q term. So but since we are rejecting it to ambient, that will become 0. So this is what we will get. So it will be 12.4 kilowatt. So that is exergy destruction. And I think one more, you have to find out exergy efficiency. Efficiency is exergy in out minus exergy in. So exergy out by exergy in. Exergy out minus exergy out by exergy in. So that will give me my exergy efficiency. I think that this slide is missing. I'll add. So with that, I have finished the problems which I have prepared for today. So I tried to cover most of the components and how to apply an energy balance across the component, and also some processes. So a combination of these components and a process, and also when we have a steady state process and an unsteady process, so how to do an exergy balance. So this exergy balance is just your combination of first law and the second law. So do an energy balance and then entropy balance and combine it together, you will get an exergy balance. So that's what we did, and that's what we did even in an unsteady process. So with that we can easily estimate the exergy destroyed. and with that we have covered the exergy portion. So next week we'll try to solve some numericals on Rankine cycle and to Brayton cycle. So with that I'll close the session for today. Thank you.